Okay, welcome everybody. I'd like to get this started with our first video called the Introduction to Rotational Inertia. What we're going to do in this first video is to derive and determine a new quantity called rotational inertia. And we're going to derive that from our original idea of kinetic energy. We're going to interpret it a little bit and give you some conceptual examples, and then we'll talk about the moment of inertia for a distribution of point masses. So to get started, let's consider a point mass that's rotating around the axis that's shown. This is rotating around a perpendicular distance r from the axis. The mass has a mass m, and I guess we're going to assume circular motion here. Now the first thing we're going to take a look at is the fact that this mass actually has kinetic energy. And we know that because it's moving in a circle, and anything that's moving has kinetic energy. So let's begin with our formula for kinetic energy, given by 1/2 times mass times the linear velocity squared. Now what we're going to do with that is we are going to do a substitution. And we're going to replace the linear velocity with an angular velocity. And so the next step here is that we're going to replace v with omega times r. And we learned the other day that angular velocity times the radius is equal to the linear velocity. So we just did a substitution. Now after this I'm going to reorganize the terms a little bit so that I have 1/2 times mr squared times omega squared. And this looks a lot more like our formula that we started with, except instead of mass we have now the term mr squared. And instead of v squared, we have omega squared. So what we have is a rotational version of our formula for kinetic energy. And it can be rewritten in this form. We're going to substitute a new symbol, the capital letter I. This is the symbol for rotational inertia. And our definition now is that we are going to define the rotational inertia of a point mass rotating at a radius r as being equal to mr squared. And this new term that we have in the box here is called rotational inertia. It's sometimes also called moment of inertia, and it's a specific formula that we came up with for a point mass around an axis of rotation at a certain distance r. Don't confuse the word moment. Moment does not have to do with time here. Moment means something acting at a distance or at a certain radius from a center. Okay, so let's come back to a simple example here. One question you might have is rotational inertia. What really is it? Well, clearly it has to do with mass, which shouldn't surprise us, but it also has to do with the distance from the mass. The mass is rotating from the center. Now let's just do a quick calculation here. This is a 1 kilogram mass rotating at 0.1 meters. You could calculate the inertia of this quantity. It would be given by mr squared, so 1 kilogram times 0.1 meters squared gives you a rotational inertia of 0.01 kilograms per meter squared. Okay, there are no special units for inertia. It's just kilograms times meters squared. They don't have any shortcut or abbreviated name. And it's a scalar quantity. Just like mass is a scalar quantity, rotational inertia is also a scalar quantity. Now the physics behind this is that the further away, you can basically do two things to increase inertia. Number one is you can use more mass. Number two is you can move that mass further away from the axis of rotation. And by doing one or both of those things, you will actually give an object more rotational kinetic energy. So let's take a look at the first thing. Let's increase the rotational inertia just simply by increasing the mass. So I'm going to replace my 1 kilogram with a 2 kilogram mass, but I'm going to keep it at the same radius. And what I've done by doubling the mass is I've doubled the rotational inertia. So an object that would be rotating at a particular omega, if it's a 2 kilogram mass, it will have twice the inertia and therefore twice the kinetic energy as the object that's shown up here. Okay, so for the same omega, the 2 kilogram will have twice the rotational inertia and twice the kinetic energy as the 1. Now, The other thing you can do to increase rotational inertia is you can take the mass and you can move it further from the axis of rotation. And by moving it further from the axis of rotation, you are increasing the inertia, and you're actually doing it even more so. Because if you go to the formula and you look at it, you find out that 1 kilogram at twice the distance actually gives you 4 times the rotational inertia that we had in the very beginning. And so increasing the radius of a rotating object is a very effective way of increasing its inertia, because as you move it further away, the inertia increases as r squared. And this is something we'll want to keep in mind. And of course you can do both at the same time. You can increase both mass and the distance from the center, and that will have even a greater effect. Okay, let's look at a couple of examples that are a little bit simpler here involving your body. And if you want, you could take a person standing up and you could basically superimpose the x, y, and z axes in that person's body. And you could talk about the fact that the rotational inertia of this person is going to be different around each of the axes that are shown. So probably the simplest axis to look at would be the longitudinal axis. That is the axis that's vertical. Now if the person were to rotate around that axis, most of the person's mass is going to be close to it. Therefore, there really won't be much rotational inertia in that situation. However, if you could imagine this person floating in space and rotating around the median axis or the transverse axis, you can see that the rotational inertia will be quite a bit greater. Because, for example, his head is quite far away from both of those axes of rotation. So, one of the ideas here is that one object can really have many different moments of inertia. It really depends on the axis that you select. There are a couple of examples here to follow with. Obviously you have a gymnast here, and the axis for rotation of the gymnast would be an axis that would be like the median axis shown in the previous figure. Okay, so it's like the axis that's coming out at us. And you can see by rolling and tucking that the gymnast is going to decrease her rotational inertia around that median axis. And so changing your rotational inertia is something that people do in sports quite often. We also see a nice example of this with a skater. And ice skaters change their rotational inertia by pulling in their arms. When they pull their arms in, they decrease their rotational inertia. If they want to increase the inertia, they can throw their arms out. They can also throw their legs out. And the idea is that they're rotating around the longitudinal axis, and when they move their limbs out, they're actually increasing the distance that some of the mass is from that axis. One other thing we want to talk about here is if you have, say, a distribution of point masses, say more than one, rotating at the same time, it is possible to determine the rotational inertia for this distribution. We know that for one point mass, the formula for the inertia is given as mr squared. If you have multiple point masses, as are shown in this picture, what you simply do is you add up the inertias from each object, and you do it piece by piece. So in this particular example, I would actually add together the rotational inertias that are determined from m1 times r1 squared plus m2 times r2 squared. And if I wanted to determine the kinetic energy of this system, assuming that both of the masses are rotating together at the same omega, I would simply take that new total inertia and I would plug it into my formula for kinetic energy. Okay, so I hope that we were able to define rotational inertia, show how it relates to kinetic energy of a rotating object, and giving you some examples of how you can use it. Okay, see you next time.